Have you ever learned something new that completely changed the trajectory of your life? Whether it be from a breaking news article, an experimental novel, or perhaps from a random podcast coming out of the University of Virginia? Some new idea or piece of information that changed your outlook on the world and how you continue to interact with it? For me, it was this book called Letters from the Underground by Abby and Anita Hoffman. This collection of letters was written in the 1970s by two youth social activists, and it sparked something up that made me want to understand how the history and politics of the past affect the world we live in today. For Professor Brad Johnson, it was this book by Kip Thorne explaining the basics of astrophysics. For a finale episode, Jason and I sat down with Brad Johnson, a UVA professor in the astronomy department. He told us the story of how he first became fascinated with cosmology.
When I was a kid, I just was really interested in it was a concept I couldn't quite wrap my head around, so I spent a lot of time thinking about it. And infinite universe, what does that mean? It was really hard to understand, so I spent a lot of time on it. And one thing led to another, and then I found out later in life you could actually do this for a living, which was kind of exciting. And so here I am doing it for a living. I think the specific turning point for me was as an undergrad. I was going to go into industry. The whole time I was an undergrad, I was going to go into industry, and I had a job lined up and everything. It was going to be great. I started reading a book by a guy called Kip Thorne, who was just here, and he gave a talk just sort of describing astrophysics and sort of all of this stuff that I now kind of think about. And it was just captivating. The book was written for popular audiences. It wasn't a textbook. And I actually only got halfway through, and I just put it down like, I'm doing this. And so I very quickly applied for grad school, and I was fortunate enough to get in. And so then I've been finding my path. And at the time, I didn't really know what I was doing, right? I just knew it was cool, and I was excited. And so I've had found my passion, but I didn't know operationally what the path was going to be for me. And so then I had to figure that out. So then it was a question of meeting with professors and finding out, what does all this mean? What can you actually do? What are projects that are actually available? So that was where I kicked it off. And so what I study in general, what I'm interested in general, is understanding the universe as a system. How does the universe work? It's a challenge, right? Because you can't go out into the universe and touch things and make measurements. You have to stay on Earth, and so you have to kind of develop detective skills to probe the universe and figure out how things work. And human beings have done quite a bit in the last 100 years. We didn't know that much, 200, 300, 400 years ago. But thanks to technologies that have been developed, we've been able to actually learn quite a bit. And so it's an exciting time for my field.
And what can you tell us about the project that you're working on now with the Jefferson Trust?
It's the Dark Matter Radio Telescope at UVA's Fan Mountain Observatory. That's the name of the project. And so there's a lot there. So there's dark matter, there's radio telescope, and there's Fan Mountain. So I'll start with Fan Mountain because that's the easy part of the story. So Fan Mountain Observatory is UVA's observatory. It's about 20 or 30 miles south of grounds. And there's a collection of telescopes there that were built in the 1960s for astronomical research. And so we have this great facility. I came to UVA about 6 years ago, and I've been trying to think of ways to use the observatory because it's there, and not everybody has access to an observatory, so it's kind of a rare resource. And so I came up with this idea to put a radio telescope there. My cosmic microwave background studies are kind of close to radio observations, and so I had this thought, we should put a radio telescope there. So I had it in my head that this was maybe a good idea, and so I was trying to figure out a way to use that resource. And then a few years ago, I got into the dark matter part. So dark matter is kind of a crazy thing. So when you get into cosmology and you start understanding how the universe works, if you look out into space, if you go out in a field at night here, you just see black and you see points of light and you think those are stars and it's kind of cool, but it's not that impressive, right? It's black. Well, it turns out what I study most of the time, the microwave background, is the black part. So it's black to your eye because you can't actually see the signals. The signals are at different wavelengths that your eye isn't sensitive to. And so the signals that we actually look at for cosmic microwave background studies, they're at millimeter wavelengths, which is kind of in between infrared and radio. So you have to build a special camera. You build a special camera, you take a picture of the sky, there's a lot to see. So that's what I do most of the time. But microwave background observations allow you to understand sort of how the universe is working. You connect the observations with theory, and you can start constructing explanations for what you see. And what you find is that, first of all, the universe is this vast place, and there are billions or trillions of galaxies, other galaxies. We live in one galaxy, which is the Milky Way, And there's billions and trillions of galaxies out there, which is kind of exciting because it's a lot of places to go. We can't go to any of them, unfortunately, but you can look at them if you build the right instruments. And so that's what we do. And if you study the dynamics of all of these galaxies, what you find is that the universe is expanding, which is kind of crazy. And so this was something that was actually predicted by Albert Einstein when he developed the theory of general relativity in the early 20th century. And so it turns out it seems to be right. The universe is expanding. There's tons of galaxies. And so if you get into the fine details of this, which the humans did over the last 100 years, you start figuring out things like, what's the universe made of? It's made up of particles, right? So the room is made up of particles. The air in the room is made of particles. Everything you can touch is made of particles. And so when I teach my courses, the way I always describe it is, it's like the universe is made of a Lego set. And there's actually not that many different kinds of Lego pieces. Each Lego piece is a kind of particle. And you put the Lego pieces together a particular way, and it looks like something. If you put them together in a different way, it looks like something else, but it's foundationally the same Lego pieces. So all the stuff that we touch, it's a particular set of Lego pieces. Quarks, they're called, quarks and gluons, and they come together to make protons and neutrons. And then there's electrons, and so these are the particles you hear about sort of in high school. And so those are the most common, so we know a lot about those. But if you keep studying, you realize that there's other Lego pieces we don't know what they are yet, and that's kind of the fun part. And it sounds mysterious, but when you actually track the story, the historical story, we've only figured this out in the last 100 years. We're alive at a time where the story hasn't completed yet, right? So the stuff we know, we're really confident in, that's done, right? But we haven't completed the full story. And so dark matter is a sort of a mysterious name given to a particle that we've detected. We know there's dark matter out there, but we don't know what the particle is yet. So we have to figure that out. That means we have to develop detective skills, right? Because again, it'd be great if you could go out in the universe and collect things and touch them, but you can't do that, so you have to come up with techniques. And so dark matter kind of lies at the interface between physics and astrophysics, I would say. There are people who are in physics who do particle physics, who study the particles I was just talking about, and they're interested in dark matter. And then there are astrophysicists who are interested in dark matter as well, and for slightly different reasons. So for an astrophysicist, when you look at the dynamics of galaxies, to explain what's going on, you need dark matter. To explain the existence of galaxies, you need dark matter. It's one of the key ingredients of the entire universe. We just don't know what it is. And so the reason we don't know what it is we can't interact with it. There would be dark matter in the room right now, but it's just passing through your body, right? It's not interacting with the cells in your body. It's just in the room. So you need to come up with a way to interact with that dark matter so you can study it. And it's fussy. It doesn't want to be studied, right? And so you have to come up with clever ways to do it. And so people who do particle physics, they have several theories out there for what the dark matter particle might be. And one of the most compelling is the axion. And so the axion is one kind of particle. And the advantage to the axion is it has a very well-developed theory, and it came out of particle physics. The particle physicists in the 1970s had a problem, and they said, to solve our problem, there must be another particle, and they called it the axion, and it was a cute name because there was a laundry detergent called Axion at the time, and it was going to clean up this problem. So they gave it this cute name. They weren't thinking of it as a dark matter particle. They were thinking of it as a solution to their particle physics problem. And so it turns out that particle has kind of the same properties as astrophysics dark matter, and so we eventually kind of thought, maybe it's the same thing, right? Particle physicists think there's axions, and astrophysicists need something like an axion. So maybe it's just the same thing, and it's just all over the place. And from both communities, the behavior of the particle is similar. It doesn't do anything, right? You don't touch it. You can't. It's not interacting with your life. It's doing nothing, which sounds crazy, but just to add a couple of data points, the sun produces neutrinos. In the middle of the sun, the way the sun works, there's fusion happening. And one of the waste products of a fusion event is a neutrino. So there's tons of neutrinos flying out of the sun. They don't do anything. They're streaming through the room right now. There are tons of neutrinos. They do nothing. If we built a sophisticated neutrino detector, we could detect all these solar neutrinos. But they're in the room. We just don't touch them. It's the same thing with Wi-Fi. Wi-Fi is light. So there are light particles that are Wi-Fi. It's filling the room. That's how your phone is working. You don't see them. They're passing through your body, and you don't know that they're there. So dark matter is kind of the same. So the axion is put on the table as one candidate dark matter particle. And the great thing about it is there's a well-developed theory. So you can develop experiments and go and probe this kind of dark matter. And so particle physicists are doing one thing. They build experiments in laboratories. And according to theory, if you take one of these axion particles and you put it in a magnetic field, it will decay into photons. And you can detect photons, which is great. It's kind of funny because it's a dark matter particle, but it can turn into light. But the trick is you need a strong magnetic field. And most of the magnetic fields in the universe aren't strong enough to trigger this conversion. So the axions just float around with nothing to do. If they encountered a strong enough magnetic field, they could turn into photons, and then you could detect that. And so what particle physicists are doing is they're trying to create magnetic fields in labs and then try to get the axions that are floating around in the room to convert and then listen for the conversion signal. But if you do all the math, the probability of this happening is really small given the fact that you can only make a field that's about 10 Tesla. So Tesla is the unit of magnetic field strength. And 10's pretty strong. You can make a 10 Tesla magnet. If you stick it to your refrigerator, you're not going to ever get it off. It's a really strong magnet. But that's about as strong a magnet you can possibly ever make. And so you make the strongest magnet you can make, and then you do the math, and you realize you're going to get sort of 1 photon a year at some frequency you don't know what it is. So it's a lot of sitting around and waiting and listening and hoping. And so the game really is, can we get stronger magnetic fields somehow? Can we push past this limit that's set by practical constraints from laboratories? And turns out that when you study stars, stars have a particular life trajectory. And you can have small mass stars like the sun. The sun is surprisingly a small star. You don't realize that because it's close by, but it's a small star. You can have high mass stars, which are much larger, and when they run their course and they die, they either turn into black holes or neutron stars. And a neutron star is all of the matter collapses down, and the protons and electrons come together to form neutrons, and you get a big ball of neutrons. And it's hot, but it's really small, so they're actually hard to see. So if you go outside and you look for one, you're not going to see one with your eyeball. You have to kind of come up with a sophisticated observation technique to look for these things. But they're all over the place because they're stars that have died, and the universe has been around for a long time, so there's a lot of dead high-mass stars out there. So if you get into the details of how neutron stars work, they have magnetic fields. They're basically a ball of neutrons with a plasma around them, and that generates a magnetic field. And the magnetic field from a neutron star is like 10 billion Tesla. So jackpot, right? You're stuck at 10 Tesla in the lab, you need a bigger magnet, and there's free magnets that are 10 billion Tesla, right? So the problem is you can't go over there and do an experiment. You got to use that as your laboratory, but you got to leave it out there in space. And so the question is how you do it. And the good news is the axions are there too, right? They're everywhere. So you've got a big magnet over there and you've got axions over there. And so all you have to do is figure out how to do an experiment from here. And so the idea is if you get an axion converting into photons through this conversion process, then the photons coming out would have some wavelength. And the wavelength, according to theory we think is correct, should be kind of in the radio range. It'd be kind of fun if it was visible wavelengths, because then you could go out there with your telescope in your backyard and you could watch these things, but it's not. So you have to have a radio telescope to look for this signal. And so the idea was to get a radio telescope, put an instrument on the radio telescope that's sensitive to spectra, so you can measure the frequency content of a signal, and then point the radio telescope at neutron star populations and see if there's any signal coming out. Because the neutron stars are emitting thermally, which is what you'd expect. But then if you look and you see some line that you can't explain, then that might be a candidate axion conversion signal. And so that would be exciting because with this instrument, if we made that detection, we would know the mass of the axion. When the axion converts into a photon, the mass energy of the axion turns into the photon energy, and the photon energy is related to the frequency, which is what you're measuring. So not only would you find that axion theory is correct, perhaps, but you'd be measuring the mass of the axion very precisely because of the instruments that we're capable of building now, thanks to all of the technological development over the last 50 years. So that's the game. So we've got the telescope, right, from the Jefferson Trust. We've got the observatory from UVA. And we've got this whole population of students looking to do fun stuff. The great thing about this project is that it's the kind of project that students can do, right? If you build a space telescope, realistically, undergrads aren't going to, touch a space telescope and launch it into space. But this is something where you can send students out with screwdrivers, and they can help us assemble it, and they can help us, collect data and analyze data. And so it's going to be a lot of fun. So the idea altogether, when you put all the pieces together, is to have undergrads help assemble the radio telescope, use the radio telescope to look at neutron star populations to see if we can find this axion conversion signal.
So let me see if I am understanding things correctly. So when you're looking into it, you're seeing the photons really, which were dark matter acted on by the neutron.
That's right, neutron star.
Neutron
That's
star.
correct.
Okay,
Yeah.
That's interesting.
Is part of it just proving that axion theory is correct?
I think that's the main goal at the moment. With all of these particles, figuring it out is the first step. And then once you know what it is, then you can start thinking about, are there clever ways to use this knowledge, right? And so, for example, with other particles, we don't know what's out there than 100 years ago. And then you start being similarly curious and doing experiments and probing around. And you say, oh, yeah, now we know it's protons and neutrons and electrons. And then you work out a theory that explains how they work, right? And then it's a predictive theory. So I can say, oh, the predictive theory tells me that if I do this, then these particles will behave this way. Mm-hmm. And then you say, oh, good, if that's true, then I can make a phone. I can make a car. I can make an LED light bulb. I can make a podcast microphone. You can start using this these technologies, or you can use the science to develop technologies. So for dark matter, we're at the stage where we don't know what it is yet. If we find it now, I don't know what's going to happen 100 years from now. I mean, it's everywhere. Maybe it's an energy source. It's filling the universe. Who knows, right? It's pretty exciting. You can start imagining things, but you don't want to put the cart in front of the horse. You got to figure out what the particle is first. So that's step 0.
I love the idea of discovery for discovery's sake. Yeah. All of us do. That's why we're here. There are people funding us to do things that want the idea of discovery for whatever, commerce's sake, human improvement's sake. Right. So I appreciate you saying what that is, because then what's the next thing? What's making the axion? That's just the endless discovery, right?
Yeah, that's right. I've enjoyed this part of the project because I understand the existing particle stuff pretty well. I'm not a particle theorist, so I'm not the expert in the world, but I kind of understand enough to feel happy about it. But what I realized is that we're really in the middle of the story. And so it's fun to think like about axions and detecting axions, but maybe it's not all axions. Maybe there's other particles too. Maybe dark matter is not just one thing, maybe it's several things. And this is all going to unfold over the next 100 years, 1,000 years. We're going to keep figuring this stuff out, which is kind of fun. And numerically, the energy content of the universe is like 5% of the stuff we know about. The stuff we're made of is like 5%. The dark matter is like 27%, which is a lot. Yeah. So it's like 5 times all of the stuff we know about. Take that, multiply by 5. That's how much of it is dark matter. We know that just from gravitational studies and looking at how things are moving around. We don't know what that stuff is. Yeah, maybe it's many particles. Maybe it's, you can start imagining all kinds of like things that start to sound like science fiction, but it could be anything. We don't know. We're at this part of the story. It's a discovery part of the story, so it's pretty exciting. And again, it's fun that it is the kind of project that undergrads can do. Like I said, if you're building a space telescope, it's built by professionals behind glass and you don't know about it, right? But this is something you can actually touch and you can work on. And so I think that's pretty exciting.
And you have your team that's building it right now of students. Are you going to integrate more students in there to do some of the watching research part, or how's that system?
Yeah, we'll definitely have more students get involved in the future. And I think there's going to be, with the dedicated telescope approach, there's going to be a lot of data. So we'll be looking for data analysis projects for students and people who want to observe, people who want to make new instrumentation. 5 years from now, there'll be some new thing that we'll put on the telescope, and it'll be a better spectrometer, different wavelengths or something like that. So there's lots of room for development in the future, advancing it in the future. And so I think there's going to be more projects. There'll definitely be space for more students.
Students interested in the dark matter radio telescope research should contact Professor Johnson directly through his UVA email.
There's a lot to do. And when you're starting out as a student, you typically have no experience, right? You're interested and the story's cool. But then the question is, what do I do? And so you have to find some entry point where you can start doing something, right? So that's usually the game. You have to match people's interests and abilities to a particular part of the project.
Pilot Projects, Stories from the Jefferson Trust is a Sound on Grounds podcast. Sound on Grounds and all of the projects featured in Pilot Projects are sponsored by Jefferson Trust grants. Thank you so much to the Jefferson Trust for supporting the Sound on Grounds program and for making this podcast season happen.
I want to say thanks to the Jefferson Trust. It's a fantastic organization, and this is my first experience with them, and what they're doing is really cool. They're trying to really get opportunities into the hands of students, and that's really what I think UVA is all about, right? It'd be fun to see if you could measure the impact on people's lives of stuff like this, because if you go 10 years from now and you ask the people who are working on the dark matter radio telescope project, or even you guys, you're working on the podcast, like, how did this affect your life? I think there's just going to be lots of ripple effects coming from grants like this, and so I think the program is really important.
You can find more Sound on Grounds podcasts at virginiaaudio.com. Today's episode was engineered, written, and edited by me, Sara Bastianelli, in the Robertson Media Center audio studio. The Pilots Project show cover was designed by UVA alum Carina Velocci. All the music in this episode was written and recorded by Jason Evans Groth in the RMC audio studio. Thanks again to Professor Brad Johnson for sharing his story with us.